Okay, so in this video, we are going to solve this problem. In this problem, in the part A, we are required to derive equation. And from this equation, we'll get the transfer function. And then we'll get the block diagram. And we know that to get any equation or transfer function, we need to identify what is our output and our input. So we know that our output is basically theta, which is our output, and our input is basically torque, right? So this is our output and this is our input. So we are going to get this transfer function in the end. Now let's just figure out what this tau of s is, because we need to first find what is our input. So we'll have torque due to force, we'll have torque due to spring, we'll have torque due to this damper. So the torque due to force is given as FL cos theta in general. And we know that our angle theta is equals to, or is approximately equals to 0. Why? Because this is given here, which means tau is equals to FL cos 0, which is tau is equals to FL. Now when this force is applied, the length becomes L by 2. So the length at which this force is applied is basically L by 2. So we won't write L, instead we'll use L by 2, because the force, when the force is applied, this moment arm in the force equation becomes L by 2, right? So we get this torque due to force. Now we need to find the torque due to spring, and we know that torque due to spring is equals to minus the distance. With force it was L, but with spring it's K. And with spring there is always a negative sign, and we write X with it, right? So minus Kx is our torque due to spring, right? And we know that in the torque due to spring equation, our X will be equals to L theta, right? Because it is because of this joint, so we get X is equals to L theta. So if we put in this value, we get tau K is equals to minus K L theta. So this is our torque due to spring. Now for the damper, we will write the exact same equation, but the damper equation is basically tau, and the damper is C, so we'll use C is equals to minus C, and because it's damper, the spring, in the spring we have X, but with the damper we have the derivative of X, okay? And the derivative of X will be given as same thing, but with the derivative of theta. Now if I put in this, we'll get tau C is equals to minus C L theta dot. So these are our three torques that we have obtained. Now, now we have a revolt joint is J. So we have theta in the equation, we have theta dot in the equation, and our theta double dot will be with the J. So J theta double dot is going to be equals to torque, which is basically our input, and we will write, so this is our torque due to force, then torque due to force plus torque due to K plus torque due to C, we add all these things, we get tau plus FL by 2 minus KL theta minus CL theta dot J double dot. I can make an equation from it. Because the theta is our output, so we bring all of them to the other side. Theta double dot plus CL theta dot plus KL theta is equals to tau plus FL by 2. So our input is torque, and our input, the additional input, is force. So we have two inputs in the equations, and we have output theta, which is theta dot with the damper, theta with the spring constant, and theta double dot with the moment arm. So we get this equation. Now if we derive this, we'll get, if we take Laplace, we'll get J s square theta s plus CLS theta s plus KL theta s equals tau of s plus f of s L by 2. Now we take theta s common here. We get Js square plus CL s plus KL is equals to tau of s plus fs L by 2. Now our output or input, so output is this, input is this whole thing in general, so theta of s divided by tau of s plus f of s L by 2 is equals to 1 divided by is equals to 1 divided by Js square plus CL s plus KL. So this is our transfer function. This was our equation that we derived. Okay, now if we put the additional input that we applied to the system, f of s equals to 0, we get a very simple transfer function of the form that we usually study. So we'll get theta s by tau s is equals to 1 divided by j square s square plus CLS plus KL. Okay, so this is the transfer function. Now if we are required to find the block diagram of this, what we need to do is we will look at the equation that we obtained here. We'll get the theta double dot from this equation. What we will do is we will keep this thing here is equals to tau plus f L by 2 minus CL theta dot minus KL theta. Okay, now I'll divide the whole thing with tau plus FL by 2 minus CL theta dot minus KL theta, and we divide the whole things with J. Now, to sketch the block diagram, the first thing that we need to do is we need to draw the summer here. After summer, we basically will get theta double dot. But if we get all the inputs here, we'll get the output fraction, which is basically multiplied by 1 by j. and then we will obtain theta double dot, right? So theta double dot will be here. So theta double dot is obtained after multiplying all the inputs with 1 over j, right? We get theta double dot. Now from theta double dot, we can get theta dot by integrating. So we put integrator here to get theta dot here. And then we put another integrator here to get theta here. And we know that our output is theta. So this is how we get the output. Now, because it is going to be the feedback path, so if we look carefully, theta double dot, the theta is multiplied with KL. Theta is multiplied with KL. So theta is multiplied with KL. And it is basically with a subtract sign. So I put an arrow to this summer with a negative sign. So we have theta minus theta KL, and then this whole thing is multiplied by j, 1 over j. So minus KL divided by j, right? We also has an input tau. So we also has an input tau, which is multiplied by 1 over j. And we also has an input f, but this input is multiplied with L by 2. Okay, so this is with plus, this is with plus. So we have theta, we have tau plus FL by 2, tau plus FL by 2, both are divided by 1 by j, minus theta KL multiplied by 1 over j. We are left with this term, and this term is basically theta dot. So it will come from this point. It will multiply with CL, and it will go to this summer with a negative sign. So now theta double dot is equals to tau by j. So theta double dot is equals to tau by j plus FL by 2 by j. These two are with plus. Theta dot CL by j, which is with minus, and theta minus KL by j. So this is how we have obtained the block diagram. So we're done with the part A. Now we move on to part B, in which we need to find the DC gain, natural frequency, and damping ratio of the system. So we'll use this transfer function for these calculations. So because we have the H of S is equals to, now I'm doing part B basically, where we need to find DC gain, natural frequency, and damping. So we're given with H of S is equals to theta of S divided by tau of S is equals to, we can write this term as well, no problem, 1 divided by J of S squared plus CLS plus KL. Now we need to make it in the form of standard second order equation, and the standard second order system has a 1 with this S squared term. So we need to remove this J from here, and for that we need to divide the whole numerator and denominator by J. So you'll get 1 by J in the numerator. If we divide this term with J, it will become S squared plus CL by J S plus KL by J. Now this is going to be our updated transfer function. Now to get DC gain, what we need to do is we need to put S is equals to 0. Okay, so if we put S is equals to 0, this whole term will become 0. So we get h of 0 is equals to 1 by j divided by kl by j. So this term will cancel, and we'll get 1 by kl. So this is our DC gain, right? Now we know the transfer function. I'm going down to solve the other parts. So our h of s is equals to 1 divided by 1 by j. This is what I obtained. S square plus CL by j s plus KL by j. And I already have obtained the DC gain. So the DC gain that I have obtained is 1 by KL. Now for the second part, we need to find natural frequency, which is basically in the standard second order system, which is the standard second order system has a denominator of s square plus 2 zeta omega n s plus omega n square. So we have omega n square is equals to this term, KL by j, which means omega n is equals to under the root KL by j. All right, now next part we need to find damping, which is zeta. So this in the second order standard form 2 zeta omega n is basically is equals to this whole term CL by j, and we know the value of omega n. So let's just first move the 2 over omega n here. So we have 2, and we have omega n under the root KL by j. Okay, now what we need to do is we need to, if I remove this under the root by j from here, I can write this as, how I can solve this is by making CL divided by j 2, and then I can write under the root KL, and this is in the division under the root j. So this is basically under the root, and this is j. So if I manipulate this, it will becomes CL divided by 2 under the root KL. This is power 1, this is power 1 by 2, so 1 minus 1 by 2 is power 1 by 2, so we'll get another under the root j. Because I solved these two, this is power 1, this is 1 by 2, so if I move this, 1 minus 1 by 2 is 1 by 2, so we get under the root above. Okay, so this is what I have obtained. In fact, I've done it wrong. In fact, this term is in the third denominator, so it will go upside. So this is under the root j, and we get this j here. So I wrote j here, 2 here, and under the root kl here, and this j moves upside. Now this is 1 by 2 and this is 1. So 1 minus 1 by 2 is again 1 by 2. So this is 1 by 2, this is 1. So 1 minus, so if I move this one down, 1 minus 1 by 2. So we'll get 1 by 2 downside. So we get CL divided by 2 under the root KLJ. Because we get 1 by 2 downside, it will become 1 by 2, means it will have an under root. So I put it inside. So we get zeta is equals to this. So that's all with this question. I hope you understand this.